Dear scientists attending the 4th ICSEI conference, my best greetings. My name is Francisco de Melo. I am a researcher of INEGI, Institute of Science and Innovation, Porto, Portugal. I am one of the authors of this work entitled A Numerical Dynamic Analysis of a Multi-Body Bus. This is a theme in the framework of structural analysis and design of public transport vehicles, a field of unquestionable importance, joining several research areas as sustainable mobility of citizens, structural assessment for integrity and reliability, efficient production engineering, numerical simulations, and this only to mention some of the almost endless fields of research for efficient and safe vehicle designs. In our cities, the option for multi-body or multi-coach buses is not totally consensual, and it is not always an excellent choice, as some drawbacks for easy circulation may affect such oversized vehicles in some urbanistic and road designs. Testing large-sized structures by experimental techniques may be an expensive task, though the more accurate and real results come from this option. It is a workful and time-consuming decision, which, despite its unquestionable importance, can be performed by alternative numerical models, also warranting reliable results if developed with good experience and trustworthy models. In the presented work, we decided by a numerical simulation bearing on the modal assessment of a double body or coach articulated bus. For this purpose, the following steps were taken. 1. Theme introduction. 2. Model characterization. 3. Numerical modeling, results discussion, and 4. Conclusions and future themes. Here we present a resume of motivation items for the research here reported. Essential details focuses on sustainable mobility, this one making the obvious choice of electric power, lightweight and robust body design, optimize the 3D frame type structures possibly, investigation of dynamic force effects on a proposed vehicle body structure. More details you can read in the present paper text. Here, this presentation is shortening the message not to be boring for you. Here is depicted a resumed description of an articulated double-body bus about its model characteristics. Each module was modeled as a solid rigid element where closely similar dynamic characteristics as the weight, 3 main coordinate axes, inertial moments, mass center position were sought to match the real vehicle body characteristics. The problem's outline enhances the attention to a dynamically coupled problem or multi-body dynamics study. Two bodies, assumed as rigid, contact the road via the vehicle suspension, being both modules connected by a specific design, towing double-hinged bar with a damping system for safe road driving control. In synthesis, numerical characteristics are the tractor body weight almost reaching 9 tons, trailer body weight 5.9 tons, total vehicle weight about 15 tons. Front module has normally the power unit, maybe a diesel engine or an electric motor. Dimensions are listed in this slide here shown. Passenger seats and interior isolation material were converted into uniformly distributed masses, while battery banks, if applicable, were considered as partially distributed masses. Proceeding with the dynamic model, we assign the equivalent spring stiffness suspension to each vehicle wheel, having worked as follows. A. Vertical spring stiffness suspension, radial load, is a series type spring association combining the radial load tire stiffness with the one due to a pneumatic vessel reinforced rubber suspension, respectively K tire and KB. B. Additional spring stiffness factors existing in the horizontal plane refer to acceleration and braking forces, and they are tangent to the tire external circumference. Also, a transverse force acting normally to the tire circumferential plane completes the force system acting on each wheel. This last force results of a drift or shear force by lateral loads acting on the vehicle. Take, for example, the effect of a centrifugal force in curved trajectories and lateral wind pressure. This stiffness and the one resulting of acceleration or braking forces have similar expressions. Procedures for model simulation. The case-in study consists in evaluating the modal spectra of two bodies linked by a partial constraint double-inch towing bar. This device allows only some free rotations, but practically prevents the relative rotation of truck, trailer along longitudinal axis, for sake of passenger safety and internal vehicle geometry conservation. All the remaining rotations, though free to occur, they have a viscous type damping forces by special actuators controlling their amplitude and eventual self-exciting vibrations. The vehicle chassis platform was modeled in simple and straightforward geometry, meeting as much as possible the same stiffness over three principal coordinate axes and similar dynamic properties: mass, center of mass, position, and inertial matrix of the real vehicle. For the purpose, finite element model got and a wide-ordered plate elements, 8 nodes on the membrane plane or mid-plane, and using 4 Gauss points along the thickness vector for matrix integration. Maximum and minimum von Mises equivalent stresses were evaluated for the chassis vehicle subjected to nominal payload and dead weight. This slide describes natural frequencies and respective vibration modes up to the 8th order. The calculation was obtained with Abacus CAE software using the subspace iteration technique. The multibody dynamic model required accurate calculation given some rigid body motions by coupled kinematics at the towing hinge bar. Such modes are associated to define the frequencies due to individual stiffness mass characteristics for the tractor and the trailer. However, the two bodies are connected and conditioned by some rotation constraints. Then, relative oscillations occur only at the vertical symmetry plane and the horizontal plane, this occurring by curved trajectories. There is no relative oscillation over the longitudinal axis of both bodies connected. This slide reminds in some sense previous data alerting the coupled bodies oscillations that are permitted via the towing double-hinged bar. It is recalled that this towing bar has two viscous type damping actuators preventing self-excited lateral oscillations due, for example, to effect of lateral wind pressure, this eventually leading to less safe straight-run driving. An additional note left here, it is recalled that frequencies higher than the 8th order previously mentioned modes reflect now the vibration of the body frames, now showing a non-rigid yet deformable body structure. Such excitations can now result from higher frequency road irregularities profile or a lesser mechanical condition of engine supports to chassis. This is applicable in case of reciprocating motors, of course. This slide discusses the influence of the damping factor of viscous force dissipation actuators fitted in the towing double-hinged bar. It is seen that a damping factor has a base value of C about 1.2 times 10 raised to 3 newtons millimeter second per radian, calculated for an angular velocity at mutual rotation of the extreme hinges, has practically no influence in the frequencies detected for the lateral oscillation or vertical oscillation of the vehicle. Conclusions and future research. It is important to note that this work does not present any novel technique or model for dynamic analysis of special design passenger vehicles, as is the case of a double-body articulated vehicle. The numerical analysis for the vehicle natural frequencies led to useful technical informations. The lowest frequencies are dependent of the suspension stiffness and damping characteristics. The highest frequencies of the vehicle dynamics are dependent of the body frame mechanical characteristics, and there is a considerable difference between natural frequencies of the vehicle suspension and those assigned to the vehicle body frame. In large size and heavy passenger vehicles, low natural frequencies are desired for sake of passengers' comfort, but this may render some instability in driving for running on less smooth tracks. Suspension stiffness control is then desirable with most recently developed pneumatic springs. Thank you for your attention. Queries may be addressed to the authors of this work, Mr. Rogério Lopes, or myself, Francisco Melo.